Hello, I'm going to be talking today about my Milestone 1 project, which I was a part of the L3 communication team on creating and detecting LPI waveforms. So what does LPI mean? Well, LPI stands for low probability of interception. Okay, so my part of Milestone 1, to prove that I did finish it, first off, I was supposed to research LPI waveforms, find out what they are, how to detect them. There are several methods of detecting them. So what it is, how to detect it, and then it was to use image processing to detect the signal, get the key parameters of the signal to show that it is indeed an LPI waveform. Okay, so first off, with the research. So there was a lot of research that had to be done. There was a lot of research. First off, I got this big book. I need to show you the book. This book had most of the information that I got for the project. Very good resource. Okay, so first off, it went into what is a radar. What is a radar? We all know kind of what a radar is. It's where you send out a signal. The signal is usually a microwave signal. You send it out, and it goes out and it hits the object, bounces back, and from that signal, from the reflection of the signal, then you are able to calculate the distance of the object, the angle, the velocity, and the size of the object. Pretty useful. But let's say in the military or in any kind of system, let's say you didn't want someone to know that you were tracking them. So what kind of a radar would you want? There's something called, that's why we have LPI waveforms. Okay. Alright, so what was developed is LPI waveforms. So our project was to first research LPI waveforms. And then we were supposed to simulate with the research team, which was Al and Riley and myself. We were part of the research team, which we were going to find out what an LPI waveform is, how to process that LPI waveform, and be able to extract key parameters that would define and say, yes, this is an LPI waveform. And then we would then pass our knowledge to the VHDL team, and they would implement it into a real system, into an FPGA. Sorry. Okay, so first off, my part was on the research. So first, I learned what a radar was, and then I learned what LPI radar was. So some key characteristics that define LPI radar and that make it LPI radar. It is, some key characteristics are it has low peak power, wide frequency bandwidth, frequency variability, and there's other design attributes like specific antenna design, like I showed in the video. Okay, so with these waveforms, or with these attributes, there are key waveforms that satisfy these requirements. Okay, so these waveforms that satisfy these requirements are, the first one is the frequency modulated continuous waveform. Alright, I talked about this in my presentation today. Basically, this waveform is, in the name it says it's frequency modulated, meaning that the frequency is changing over time. This makes it so it's hard to detect. And the key parameters that are needed to detect it are the bandwidth, modulation period, modulation bandwidth, and the carrier frequency. We know the bandwidth. Bandwidth is the range of frequencies that are used in the signal, and which I will show in a later slide, just like I showed in the presentation today. And so the next one is the Frank codes. Frank codes is another popular signal that's used for LPI waveforms. And just like there's carrier frequency, frequency bandwidth, code period, and slope. And okay, moving on, we have the Costas codes. Costas codes is really popular. And the reason why is because it is very hard to detect. It is the most random that we know of basically what happens is the signal is not only on one carrier frequency. It jumps. It's called frequency hop sequence, where it switches from, let's say, 1 kilohertz to 4 kilohertz to 5 kilohertz, and it keeps switching back and forth. And it happens so fast, it's hard to detect that. But there is some success with the distribution, the time frequency analysis that we've done, and that we are able to get these parameters. So there are promising results from what we're seeing in our simulations. Okay, next. Okay, this is kind of what I did, and I want to show you in MATLAB. This is proof of that I have completed milestone 1, which again, my milestone 1 was first doing the research, so understanding radar, LPI, and the different waveforms, and then to understand a little bit about the different distributions. And I need to explain, so first off, what happens in the receiving end of the signal to detect an LPI waveform is first the frequency is usually very high. Just like any signal, when it's modulated, it's usually a higher signal. Okay, so on the receiving end, we can't really process that really high frequency signal, that very high frequency signal. So what happens is the signal is down frequency to an intermediate frequency, which is called IF, and then from there it is demodulated. From the demodulation, then it goes, before that, and then it goes to an LNA, a low noise amplifier, makes it into a larger signal that you can actually work with. Okay, and then after that, then you do the processing, the digital signal processing. So first you have to digitize it. You sample the analog signal with an analog to digital converter, and then you do the DSP, the digital signal processing. And in that processing, and then we have the Choi-Williams distribution, the time frequency analysis. And first off, we know that we can't only look at the time domain. We can't only look at the frequency domain. If we just had the frequency domain, and then it wouldn't be enough, because with these signals, the FMCW and so on, all these signals, we would need to know at what time the frequency was what it was. So what do? We do a time frequency analysis. So time frequency analysis kind of shows at what time the frequency has the strongest strength. So there's a power spectral density that is computed. Okay, so now we know a little bit about time frequency analysis. The exact time frequency analysis we were doing is called the Choi-Williams distribution, which it was gone over in our presentation today from Al. He did a good job of doing that, but from what I did is I went from the Choi-Williams distribution to plotting the results. And the reason, going back to my goal was to go from the Choi-Williams time frequency analysis into an image or a picture that you can interpret and get these exact parameters from. Basically, it takes the equations and makes so you can actually understand them. And so someone, excuse me, okay, so that anyone could look at the results and interpret them, and to see that yes, they are indeed working with an LPI signal. Okay, so let me just show you my MATLAB code. Okay, here's MATLAB, and I use the detecting and classifying low probability of intercept radar quite a bit. It was a very good resource in knowing how to code this. So first, what I do is I load the signal, and then there's the sampling frequency. I split the signal up into the in-phase part. You can see right here. There's the signal is split up into two parts: the in-phase portion, and then there's the out-of-phase portion, the I and the Q. Okay, and with the Choi-Williams distribution, typically it's very it's very time consuming in the amount of calculations it takes, but there is a trade-off. It is time consuming, but it is very accurate and is very easy to get parameters out of it. Okay, so this part of the code is where I split the signal. I cut off some of the signal so it won't go through so many computations. Okay, and just a few more things. Just doing the time frequency analysis. I do the Cho-Williams. So this part is what Al did. He did the Cho-Williams, and then after that, then I was able to make from the Cho-Williams plot the results using the power spectral density function and so on. And here's all the code for that. And anyways, from the results, we can see that here are the results for. So first, I use the signal generator from the LPIT generator from the book, and here are the results. Okay. Okay, so from here, this is a power spectral density of the function, or of the signal, the FMCW signal. You can see pretty clear that it's a 3 kilohertz carrier frequency. 3 right there. You can the most of the energy is in the 3 kilohertz. Okay, and with the other part, right here, with this plot, you can see pretty clear. Remember, the key parameters that we were after was the modulation period, the carrier frequency, and the modulation bandwidth. And from this plot, it's pretty easy. It's pretty clear on what the carrier frequency is. It's right in the center. Right in the center, you can see that is the carrier frequency. So it's 3 kilohertz. Modulation bandwidth, it is the difference between this top frequency versus the bottom frequency. That is the bandwidth. Okay, the modulation period. That is the difference between this peak and this trough. Okay, so with those, so my goal was to be able to plot these results and interpret them in a meaningful way. So from this, I can know that yes, this is an LPI waveform because I can match it up to known LPI waveform parameters. Okay. Again, through my research, we looked at Cho-Williams. We looked at the cyclostationary processes. The Cho-Williams was a lot easier to extract the parameters from. Here's some of the code for the cyclostationary in getting the plots. And okay, going back to my slides. So I showed this in class, but I'll just show it again. So here's the results from the FMCW, the Frank codes. You have the carrier frequency, the bandwidth, and the modulation period. And you can see the slope as well. Okay, Costas codes waveform, we're able to, with the Cho-Williams distribution, we're able to see which frequencies hopping sequence is being used. You can see here is 3,000, 2,000, 6,000, 4,000, 5,000, and 1,000. And cyclostationary processes, from the images we can see the carrier frequency, bandwidth, and the modulation period. Okay, that is about it. So for my milestone 1, again, what I needed to do was to research, and I did a lot of research in finding out what an LPI waveform is, what radar is, and the different processing techniques on what would be the best to be able to extract the key parameters that show that it is an LPI waveform. And I was also to do the image processing part, and I've shown that yes, I did code the MATLAB, or make the MATLAB code that would get those plots for the Cho-Williams. And then we also got the plots for the cyclostationary. And then got plots, able to extract the parameters from the plots and interpret them in a meaningful way. And I think that's it.